Okay, let's unpack this. I want you to close your eyes for a second. Unless you're driving, please don't close your eyes if you're driving, and picture something for me.
All right.
When I say the word iron, what is the absolute first image that pops into your head?
For most people, it's probably a cast iron skillet or maybe a bridge. Something heavy, industrial, reliable.
Exactly.
Yeah.
Heavy, industrial. Or if you're a massive pop culture nerd like me, you think of Tony Stark.
Ah, yes.
You think of Iron Man. You picture the cool, tech-savvy billionaire Avenger flying around in a suit that is cutting-edge, high-tech, and just leading the pack.
The guy who solves the problem.
He's the guy who solves the problem when everyone else is stuck. But here's the reality check, and this is where it gets really interesting.
The Hollywood version versus the chemistry lab version.
Totally. In the actual world of high-stakes chemistry, and I'm talking about the chemistry used to build life-saving drugs or advanced plastics, iron has been, well, a bit of a B-list hero.
It's true. It's clunky. It's hard to work with.
It's the Hawkeye of the periodic table. Useful? Sure. You're glad he's there, but he is not who you call when you need to take down Thanos.
That is a surprisingly accurate metaphor. While iron is the absolute workhorse of our planet, it makes up something like 93% of all global metal production by weight.
93%.
Yeah, it's huge. But when it comes to delicate, complex chemical synthesis, it gets completely overshadowed.
Right.
The real superstars in the lab, the ones winning the awards, are the precious metals. Palladium, platinum, iridium.
The fancy stuff, the jewelry store metals.
The expensive stuff.
Yeah.
Think of them as the high elves of the periodic table, if we're doing a Lord of the Rings thing.
Oh, yeah, I like that.
They're elegant, they're powerful, and they are exceedingly rare. And chemists love them because they are predictable. They do exactly what you tell them to do. Iron, on the other hand...
It just wants to rust.
It wants to sit on the couch and oxidize. Exactly.
But that dynamic, that hierarchy where iron is the underdog, that might be about to change.
It is changing.
We are looking at a brand new paper published in the journal Science, which is like the Super Bowl of science journals, that effectively gives our B-list buddy a massive upgrade. It turns iron into the superhero it was always meant to be.
It really is a fascinating shift in how we think about catalysis. We're doing a deep dive today into a paper titled Ferrioxalate Photocatalysis, a multitasking platform for reductive iron catalysis.
That's a bit of a mouthful, I know. Ferrioxalate photocatalysis.
It is.
But stick with us because the implications here are actually huge for everything from medicine to the environment.
It is groundbreaking work coming out of the Universidad de Murcia in Spain. We have to give massive credit to the team here. Carlos Bernabeu, Sergio Adelaide, Fabio Julia, and our colleagues.
And what they did is just brilliant.
They've essentially figured out how to take a chemical reaction that undergraduate students do just for fun, zap it with a glorified flashlight, and solve a massive problem in sustainable chemistry.
Welcome to the Deep Dive Lab, everyone. Our mission today is to understand how these scientists pulled this off. How do you take the most abundant, sort of boring metal on Earth and make it do things that usually cost thousands of dollars an ounce?
It's a story of hiding in plain sight. It involves rethinking knowledge that's been around for 130 years and using light to unlock potential we just didn't know was there.
So let's set the scene properly. Every good story needs a villain, right? Or at least a major obstacle. The problem here is how we currently make stuff. Like, building a molecule isn't as easy as snapping Legos together.
Correct. Let's say you want to manufacture a new drug or a complex organic material. You need to stick molecules together. Specifically, you often need to create carbon-carbon bonds.
That's the backbone.
That is the backbone of organic chemistry. To do that, you need a catalyst, something to make the reaction happen without being consumed by it.
And right now, the go-to catalysts are those high elves we talked about, palladium and nickel.
Exactly. And the problem with relying on them is twofold. First, cost and scarcity. These metals are incredibly expensive. Palladium prices can fluctuate wildly, sometimes costing more than gold.
And they're hard to get.
A nightmare for the environment to mine. And second, toxicity.
Right, because if I'm taking a pill for a headache, I don't want heavy metals in it.
Precisely. If you're making a medicine, you cannot have even trace amounts of palladium floating around. There are strict government regulations, so you have to scrub it out.
Which costs more time and energy.
And creates toxic waste.
So it's like trying to build a Lego castle, but the only people who can help you are these high-priced consultants who charge $500 an hour and then leave toxic sludge on your carpet when they're done.
That is a very vivid image, but yes, That's the industry standard right now for a lot of these reactions.
So this begs the obvious question. Why haven't we just swapped them out for iron sooner? It's dirt cheap. You said it's 93% of metal production. Why aren't we using the Legos we already have lying around?
Because iron is stubborn. In its natural state, it is very stable. It likes to be iron in the heart. Think rust.
It's happy there, comfortable.
Exactly. To make it active, to make it ready to build those bonds, you have to force it into a reduced state. You have to add electrons to it.
And I'm guessing iron doesn't want to take those electrons.
Not without a fight. Traditionally, to get iron ready to work, to get it into that low valence state where it's reactive, you have to hit it with incredibly harsh, dangerous chemicals.
Like what?
We're talking about things like Grignard reagents or sodium-mercury amalgam.
Sodium mercury sounds like something that would get you kicked out of a high school science fair immediately.
Oh, absolutely. It's nasty stuff. Dangerous to handle, difficult to dispose of, just unpleasant. So using iron has historically been like trying to recruit the Hulk.
Oh.
Yes, he's effective once he's angry, but you might destroy your entire lab or the city trying to get him to come out.
Right, you're provoking the beast. You're using a sledgehammer to fix a watch.
Exactly. It's not practical for delicate drug manufacturing. You risk breaking the very molecule you're trying to build because the activation method is so aggressive.
Okay, so we have a dilemma. We want to use iron because it's cheap and green, but activating it is dangerous and messy. Enter the team from Spain. What was their hero weapon? How did they solve this?
They use something called ferrioxalate.
Ferrioxalate. Sounds like a villain from a 60s cartoon. Beware the ferrioxalate.
It does have a certain ring to it, but it's actually incredibly common. And here's the twist that I love about this paper.
What's that?
This isn't new stuff. Ferrioxalate has been known to science for 130 years.
130 years. So this isn't some newly synthesized quantum material.
Not at all. Since 1895. In fact, it's the standard canal of photochemistry. For over a century, chemists have used this compound just to measure light.
To measure light, like a ruler.
Precisely. If you wanted to know how bright your UV lamp was, you'd use the decomposition of ferrioxalate. It's a process called actinometry.
Wait, hold on. So for 100 years, scientists have been using this stuff just to calibrate their instruments.
Yes. They knew it reacted to light, that was the whole point, but they effectively pigeonholed it. They saw it as a measuring tool, not a manufacturing tool. They never thought to use that reaction to actually build anything complex.
That is wild. It was the Clark Kent of chemicals all along, hiding behind glasses, looking boring, while everyone ignored the Superman suit underneath.
That is a perfect analogy. It was literally sitting on the shelf in almost every photochemistry lab in the world.
So how does the transformation happen? How do we get the suit on? How do we go from measuring stick to master builder?
It works through a process called ligand-to-metal charge transfer, or LMCT.
Okay, let's unpack that. No jargon. How do we visualize this?
Think of the ferrioxalate molecule. You have the iron atom in the middle. Surrounding it, holding onto it, are these oxalate molecules.
Okay.
Think of the oxalate as a little battery pack attached to the iron.
Got it. Iron wearing a battery backpack.
Now, you hit it with visible light. In this paper, they used simple blue or purple LEDs, just high-power LEDs.
The same tech in my house, basically.
Pretty much. When that light hits the molecule, the oxalate gets excited, it absorbs that energy, and it decides to sacrifice itself.
A noble sacrifice.
Indeed. The oxalate breaks down, it physically falls apart, turns into CO2 gas.
So it just bubbles away.
It bubbles away harmlessly, and crucially, as it breaks, it dumps 2 electrons directly onto the iron.
So the light triggers a transfer of power, the
Yeah.
charge transfer.
Exactly. It turns the boring, stable iron into a superreactive, reduced iron species.
It's almost like the Force in Star Wars.
How so?
Think about Obi-Wan Kenobi. He sacrifices himself, disappears. But in doing so, he motivates Luke and makes the whole team stronger. The oxalate fades away, bubbles off as CO2, and the iron becomes more powerful than you can possibly imagine.
I actually really like that. Yes. The byproduct is just gas, leaving behind a supercharged iron atom ready to do some serious chemistry.
And because you're using light, you don't need those nasty Hulk smash chemicals. You just need a light switch.
No Grignard reagents, no mercury, just light.
That is so elegant. Yeah. So we have this super iron. It's powered up. But potential is one thing, results are another. What did the authors actually do with it?
They built a lot of things. This wasn't just a proof of concept, it was a flex. They demonstrated 5 distinct methodologies showing this is a true multitasker.
Give me the highlights. What's the biggest wow factor here?
The first one that jumps out to any chemist reading this is dehalogenation.
What means?
Ripping chlorine or bromine atoms off a carbon ring. Imagine you have a complex molecule, but there's a chlorine atom stuck to it where you don't want it.
Okay.
Removing that is notoriously difficult. It usually requires an immense amount of chemical energy around -3 volts.
It's a lot. -3 volt.
It's huge. It's like trying to pull Excalibur from the stone. Most catalysts just aren't strong enough. But this ferrioxalate system, it did it easily.
It's like using a Jedi mind trick. You wave your LED light, and the chlorine just leaves.
Basically, yes. And that matters because that kind of precision is essential for cleaning up environmental waste or modifying late-stage drugs. And speaking of drugs,
They made some?
they synthesize precursors for actual pharmaceuticals. They reference compounds 5 through 12 in the paper, and they showed they could build these complex structures even when the molecules had sensitive parts,
Sensitive parts.
functional groups. Think of them as fragile glass windows on a building. If you use the old Hulk method, you smash the windows while trying to build the door.
But this method is gentle.
The windows stay intact. Strong, but gentle. But here's where it gets really interesting. They did something called a reductive Heck coupling.
Reductive heck. Sounds like a German dance move from the 80s.
It does, doesn't it?
Yeah.
But it's actually a famous method for sticking carbon chains together. Usually this reaction requires dangerous hydrogen sources.
Pressurized gas, things like that.
Exactly, or toxic silanes. But with the iron method,
What did they use?
they used water.
Just water. Like from the tap.
Well, distilled, probably, but yes, H2O. Or simple alcohols. The reaction is so robust that they could use water as the hydrogen source.
Oh, that feels like a game changer. Usually water is the enemy of these reactions, isn't it?
It is the arch nemesis. Normally, if you get water in a palladium catalyzed reaction, or especially with those Grignard reagents, you ruin everything.
It fizzles out.
Or explodes. You need these sealed chambers called glove boxes to keep moisture out. But here, the iron system just drinks it up and uses it to finish the reaction. No toxic sludge.
That's incredible. It makes the chemistry so much more accessible. But I saw a term in our notes that sounded like a spell from Harry Potter. Umpalung.
Ah, yes, Umpalung. It's German for polarity inversion.
Umpalung. I love saying it. What does it actually do?
This is the Doctor Strange moment of the paper. This is where reality bends.
Okay, I'm listening.
In chemistry, molecules have personalities. Some are electrophiles. They want electrons. They're hungry for them.
They're hunters.
Right. And some are nucleophiles. They want to give electrons away. Usually, a molecule called an enun is an electrophile. It hunts for electrons.
Okay, enun equals hunter. Got it.
But when you use this ferrioxalate catalyst, it flips the script. It performs unpolling. It turns the enone into a nucleophile.
So the hunter becomes the hunted.
Exactly. It flips the polarity. It's like entering the mirror dimension in Doctor Strange or the upside down in Stranger Things. The laws of standard chemical reactivity seem to reverse.
So wait, this lets you snap puzzle pieces together in ways that were impossible before.
That's it. Usually, two electrophiles would just stare at each other. They wouldn't react. But if you flip one of them using unpolling, suddenly the dash click, they bond. It opens up a whole new universe of shapes you can build.
And all of this, the Jedi mind trick, the water-based bonding, the Stranger Things polarity flip, this all comes from a chemical that's been on the shelf for 130 years.
That's the beauty of it. The paper highlights that despite being known since 1895, this process was applied almost entirely for photophysical purposes, measuring light, not for making things.
It was boxed in by its own utility. It's crazy to think about what else is just sitting there, misunderstood.
It really is, and the implications are huge. Think about the democratization of science.
What do you mean by that?
Well, right now, to do high-level organic synthesis, to invent a new medicine, you effectively need a budget like Bruce Wayne. You need palladium, iridium, specialized glove boxes.
Millions of dollars in startup costs.
Right. But with this method from Bernabeu and Adelaide, you need iron, you need oxalate salts, which are incredibly cheap, and you need some LEDs you can buy at a hardware store.
So you don't need Bruce Wayne's bank account. You just need Tony Stark's creativity.
Exactly. It lowers the barrier to entry. It means labs in developing countries or smaller universities, like the one where this was discovered, can compete with the big pharmaceutical giants.
That is the ultimate science for the people moment. It's empowering.
It is. The authors point out that iron makes up 93% of mined metals. If we can shift our chemical industry from relying on the 0.001% of rare metals to the 93% of iron, that is a sustainability victory on a planetary scale.
It's like realizing you don't need vibranium to save the world. You just need to be really, really clever with steel.
A perfect summary.
So let's recap this deep dive. We started with a B-list hero.
Iron, the rusty, reliable workhorse that everyone underestimated.
We gave it a superhero suit using a 130-year-old standard candle called ferrioxalate and some purple LED lights.
Using ligand-to-metal charge transfer to pump it full of electrons, mimicking the power of much more expensive metals.
And with that, we performed chemical miracles. We stripped armor off molecules, built drugs using water, and flipped the laws of attraction upside down with impulling.
All while keeping the process green, cheap, and accessible. It solves the toxicity problem and the cost problem at the same time.
It's an incredible story. It just goes to show that sometimes the biggest breakthroughs aren't about discovering something new on Mars.
No.
They're about looking at the dusty bottle on the bottom shelf and asking, hey, what if we shined a light on this?
That is the essence of scientific discovery. Not just seeing new things, but seeing old things with new eyes. That's what Burnaby, Adelaide, and Julia did here. They looked at an old ruler and saw a magic wand.
I love that. All right, before we sign off from the Deep Dive Lab, I have a question for you and for everyone listening.
Let's hear it.
We talked about how ferrioxalate was used for over 100 years just to measure light, when it secretly had the power to create medicine. It was pigeonholed. It was underestimated.
It was trapped by its own competence.
So here is the question for you. What useless fact or boring skill or B-list talent do you possess that might actually be a superpower in the right context? Are you the ferrioxalate of your office?
That is a profound thought. Maybe your obsession with organizing spreadsheets is actually the key to solving a global logistics crisis.
Or maybe your encyclopedic knowledge of comic books is exactly what's needed to explain complex science.
Or maybe your knowledge of 80s German dance moves is just what we need to explain chemical reactions like the reductive heck.
I knew that was coming. Thanks for listening, everyone. Don't forget to hit subscribe to the Deep Dive Lab for more mental upgrades and surprising science.
Stay curious.
See you next time.